Okay, welcome everybody to week 4 of the life insurance mathematics course. I hope you're doing well. I hope your activities, the progress that you make with this course and with the other courses in your program is going smoothly. And do not hesitate to contact me or to contact one of the TAs if you're having particular struggles with the lecture material. So my plan for today is to continue with chapter 5 on life annuities. I will first do a brief recap using the iPad of what we learned on Thursday regarding the valuation of a whole life annuity due. And I will continue using the sheets with different types of life annuity products. And during the break and also at the end of the session, I will take some time to answer the questions that you may still have with respect to the organization of the midterm, right? So let's get started. So I'm going to start from here using my screen over here. And I would like to give you a recap on the whole life annuity due, which we discussed and introduced as well on Thursday last week. So it's a life annuity product. So that means that this product is offering the policyholder a certain cash flow contingent on the survival of the policyholder. So you need to be alive as a policyholder in order to receive this cash flow. It's a whole life annuity product, so that means that the cash flows go on for the rest of your life. It's an annuity due, that means that the cash flow is paid at the beginning of the year. And we're going to work here with the discrete time product to start, and we're going to work in periods of 1 year, so it's an annual time grid, let's say. So we learned last Thursday that if I look at a policyholder age X at time 0, and if this policyholder dies between age X plus K and X plus K plus 1, then this particular type of annuity products will pay payments at time points 0, 1, 2, and so on. And the last payment will be paid at time K, right? Because our policyholder dies between time K and K plus 1. There was a payment at the beginning of the year, so the very last payment is at time K. So that means if I look at this cash flow stream, then I've got K plus 1 payments in total, right? K plus 1 payments in total. And what is this K? Well, if you write it with a random variable, that means if you're going to look at the random variable kx, so here it means that the current future lifetime, the kx, takes the value equal to small k in this particular example. So with a random variable notation, I could say that the number of payments that the policyholder receives under this particular contract is equal to kx, capital Kx plus 1. So if I'm asked here to write down the present value of my cash flow stream, the present value here can be written as a double dot with duration k plus 1. So what does this mean? This is the notation that we introduced for an annuity certain. An annuity certain that pays at the beginning of the year, right? And here the k plus 1 refers to the number of payments that this annuity certain is paying me. So in total, there are k plus 1 payments. In this particular case, where the current future lifetime takes the value k. So for this particular case, this is my present value notation, right? So this holds if the kx is equal to k. So in general, for this particular product, I could say that the present value random variable is a double dot kx plus 1, right? So I'm going to rely on what I know for annuity certains, but I'm going to say, well, what is different here is that the number of payments is stochastic, and I can indicate this or I can refer to this number of payments with kx plus 1. So what is of interest to me as an actuary is, what about the EPV of this product? So what about the expected value of this present value random variable? Well, the EPV of the product then becomes the expected value of what I had over here. So that's this guy. And I know from what we learned for annuity certains that boils down to calculating the following expected value, right? And if I then connect to what I learned for a whole life insurance in discrete time, I end up with the following EPV formula for a whole life annuity due that is issued to an X-year-old. Okay, so that's my EPV. Now, sometimes students ask me, why are you particularly interested in this EPV? Well, that has to do with how we're going to charge premiums for these particular life annuity and life insurance contracts. So it turns out that this expected present value, that will really be the key element to determine what the price of this product should be in a real life setting. So don't worry too much about that yet. We're going to extensively discuss that in the next chapter, which is the chapter on premium calculations. So there you will really see that this EPV is the thing you would start from when you're calculating the price that you should charge to a portfolio of policyholders to whom you wish to sell this type of contracts. Now, we made one particular comment on Thursday, which is very important. Namely, if you are using this type of reasoning to come up with the EPV of a whole life annuity, then you're relying on the assumption of constant interest, right? And this may not always hold. So we use the constant interest assumption here, and we use it more specifically at this point, where we say, using our knowledge of summation formulas, of calculating the sum of the first certain number of terms from a geometric series, at the point where we use that, so that's over here, then we're really relying on our assumption of constant interest. Yeah? So be aware of that. We also discussed an alternative approach to put together the EPV if you want to go beyond this assumption of constant interest. And that was using the so-called indicator approach. So with the indicator approach, we said, well, we set the present value random variable y for this particular product can be written as such. So we've got an indicator function which will check the condition whether the tx goes beyond a certain value, something like this, right? And if you then take the expected value of this y, what you are essentially doing is you're looking at the expected value of a Bernoulli random variable, and the Bernoulli random variables over here are this one, this one, this one, etc. So if we look at the expected value of a Bernoulli random variable, we're using the probability of success. So that in this case boils down to using these survival probabilities, right? So if I build up this reasoning, then I'll get the following EPV expression for my whole life annuity due, and I can write that as a sum over k running from 0 to plus infinity, v to the power k multiplied with kpx. And the international actuarial notation for this is the A double dot to indicate that it is an annuity product which pays at the beginning of the year. And now I've got the subscript x to refer to the fact that it is a life annuity issued to a policyholder hx at time 0, right? So in particular, for me personally, building up this reasoning, where I look at this type of valuation formula for a whole life annuity due, that would be my preferred strategy to look at the EPV of this particular product. I would rather use this one instead of the reasoning on the previous sheet, which relies on the assumption of constant interest and which connects the EPV of the annuity product with the EPV of a whole life insurance product. So both are interesting, but particularly the second one gives me a lot of flexibility if I want to change the interest rate structure, if I want to change the benefits, if I want to make them variable over time, etc.